Thank you very much. Thank you very much. So we are going to continue where we left off. It is unfortunate that. Okay, I'll let you settle down before we start. Please make sure that you have muted your microphone so that we don't hear any background noise. Please mute your microphone. Okay. Okay, so it is unfortunate that UTM now, as you have already known, UTM now is in red area of COVID-19, so everybody has to work from home. I'm working from home right now, so I don't have access to my magic whiteboard. So we're gonna have to improvise here, but I have pre-written my notes. I'm not sure how are you going to like it, but we have to make do maybe for the next 2 weeks. I won't be able to go to office and have access to my whiteboard. But anyway, we are going to continue where we left off last time. So we already discussed about this transfer function. Transfer function is basically the ratio of the output over the input in terms of Laplace transformation, in terms of Laplace variable. If we are only interested in the input variable and output variable, all we need is just the transfer function. But we can also extract this transfer function from our block diagram. Our block diagram shows the relationship between all the variables, but we can simplify the block diagram, just get the relationship between the input and output, and therefore we are going to get our transfer function. So since our block diagram is not the same for everybody, but when we simplify our block diagram, we are going to get the same transfer function. After this, we are going to solve the system response using the transfer function that we get. Okay. So today we are going to learn about the simplification of block diagram into a single block so that we can get a single transfer function that only relates the input and output. So today we are going to learn simplification of block diagram. Okay, so there's some description there. What we are interested in is to reduce our block diagram into a single block. Then you can use this, what we call the block diagram algebra. You just look at the table here. So these two are equivalent. So here on the left-hand column is equivalent to on the right-hand column. If you have two summing junction, you can interchange the summing junction. See, when you either plus or you can add the first signal and then the second signal, or you can add the second signal and then you add the first signal. It will not make any difference. It is just equivalent. You can also split a single summing junction into two summing junctions. You can add together both signal, or you can add one at a time. So we say that this is equivalent. Most of the items in the table are self-explanatory. Okay, for example, here, if you have a block in series, then you can interchange them. This is just multiplication of two blocks, G1 and G2. You can replace with G2 and G1, and you can also just replace with a single block, which is just multiplication of G1 and G2. That is just self-explanatory. Okay, here also you can move the summing junction from behind the block to in front of the block, as long as you don't change the signal. So here C is A minus B multiplied by G. In this case, C is equal to A multiplied by G minus B multiplied by G, it produced the same signal. So we say that these two block diagrams are equivalent. You can replace the two block diagram without changing the original block diagram. Okay, you can also move the pickup point from behind the in front of the block to behind of the block. You can see that C here is just A multiplied by G for both. Okay, you can move from behind the block to in front of the block by multiplying 1 over G. So here you get A multiplied by G multiplied by 1 over G, so you get back the original signal A. Everything here is just self-explanatory. Again, here you can move the summing junction from in front of the block to behind of the block. But the signal here, previously you don't multiply by G, and then you're going to multiply by G. Since you're going to multiply by G, to make the original signal is not multiplied by G, so you multiply by 1 over G. So every time you can move a summing junction from in front of the block to behind of the block. If you have two parallel blocks, then of course this is just a summation of two blocks, just G1 plus G2. So what I want to explain further is the last element in the block. See, every time you see this feedback loop, you can replace with this equivalent block diagram. So I'm going to explain further here. So this is where I need my this is where I missed my magic whiteboard, but don't worry about it. I have pre-written my notes. Okay, so now if you have this, imagine that this is our whiteboard, and by the way, you don't have to copy copy notes today. Probably as long as I'll be working from home, I will post these notes to your e-learning after class. You don't need to make you don't have to copy any notes today. Everything will be posted on your e-learning. See, we have this feedback loop, and then we have this signal R and C. R is the input, C is the output. And then we have two more variables, Y and Z. You can simply write Y. Okay, you can simply write C is equal to G multiplied by Y, and the signal Z is C multiplied by H from the block diagram, and then Y is just R minus Z. So from the block diagram. So we have these three equations, and then we can eliminate. If we are interested in only R and C, from these three equations here, you can eliminate Y and Z. Okay, so 3 and 2. Okay, so you just put 3 in and 2 and then solve for C over R, which is output over the input. And this is the transfer function. So we say that you get G divided by 1 plus GH. And then we can say that these two block diagrams are equivalent. Every time you see this a feedback loop, you can replace that with G divided by 1 plus GH. G is the forward transfer function, H is the feedback transfer function. All right, so, do you have any question? So we are going to use this table, the table that we have discussed before. Here, this table, when we want to simplify our block diagram. So now let us simplify some block diagram to get the transfer function. Okay, let's take a look at this. Example 2. So consider this translational mechanical system. Of course, when we develop the block diagram, we get something like this. And then we want to simplify this block diagram into a single block using all the block diagram algebra. So how can we simplify this? It is not quite clear, but here you see this is a summing junction. You can split that summing junction into two. the takeoff point now, you can take the same from the same signal. I'm going to redraw this. All right, so let's go to my notes. Okay, now see, I'm going to redraw this diagram. I'm going to split the summing junction into two, and then I'm going to split the takeoff point. Okay. So this is now splitting two summing junction and then just splitting the takeoff point. So this block diagram is equivalent with the original block diagram. I haven't done anything yet. I just split the summing junction and taking the takeoff point at two different points. And then if you see here, the one that I have enclosed in red dotted line, you see this is just a feedback loop. So G is 1 over md square, H is equal to CD. So you can replace this with G divided by 1 plus GH. So G is 1 over md square, 1 plus GH, and then you can simplify that, and then you get 1 over md square. So you can replace 1 over md square plus CD. So you can replace the whole thing in the dotted red line with just a single block. Okay. So that is the idea of block diagram simplification. So that feedback loop now is being replaced by a single block. How do I get that? So because a feedback loop you can replace with G divided by 1 plus GH. In this case, G is 1 over md square, H is CD. After you have done that, then you see now this is another feedback loop. So this is the forward path G, is a more complex equation, and now H is just K. And you just repeat the process. Okay, repeat the process, and then now your G is 1 over md square plus CD, your H is K, and then you can now simplify that into a single block. So this is what we call the transfer function that relates input to the output. You just replace the D operator with Laplace transformation S, Laplace variable S, and then you get your transfer function. Okay, that is the idea of block diagram simplification. Do you have any question? All right, so let us go to the next question. Next example. All right, so example 3. So produce the system transfer function using block diagram simplification method. So we have this block diagram. This is a block diagram that we have. Okay, how are we going to simplify this? Okay, so we have this. This is not exactly a feedback loop because you have summing junction there. This is also not exactly a feedback loop because you have input here, you have another output there, another output there. Okay, so you're going to need some practice to see what you need to do. So here, probably if we move this takeoff point from behind G2 to in front of G2, and then probably we're going to have something. So my idea here is to move this takeoff point from behind G2. I'm going to move that to the front of G2. So therefore, that signal must be divided by G2, because if we take from in front of G2, the signal has been multiplied by G2, and then you need to divide it again by G2. Okay, so let's go to my notes again. All right, so this is the original block diagram. I'm going to move this takeoff point from behind G2 to in front of G2. And then that signal must be divided by G2, because originally there's no multiplication by G2, but when we take in front of G2, that signal has been multiplied by G2, therefore you need to divide it by G2. After doing that, now you can recognize that this is a feedback loop. You can simply replace that with G2 divided by 1 plus G2H1. Okay, everything in the red dotted line can be replaced with G2 divided by 1 plus G2H1. So that is the idea of block diagram simplification. See, my life is a lot simpler now because I don't have to draw everything on the whiteboard. We're going to save some time. I'm beginning to like this. Okay, so we're going to save some time here, so that I can do something else instead of drawing on the whiteboard. Okay, so now we can replace the one that is in a dotted line with G2 divided by 1 plus G2H1. Okay, but here now you have two block in series. Two block in series, you can just multiply them. You can multiply two block in series. Okay, so when you multiply that, so you have G1, G2 divided by 1 plus G2H1. Just multiply these two block in series. Now again, finally, you have this a feedback loop. Your forward path is this quotient here, and then your feedback path is H2 divided by G2. So the whole thing here can be replaced using the last element in the table, which is a feedback loop. For now, you can get the final block diagram. So this is now after we have simplified into a single block. So this is the transfer function that relates only input to the output. So the transfer function is just the ratio of the input of the output over the input. Do you have any question now? If you have any question, you can type in the chat box. Oh, we can save a lot of time doing this. Maybe some of you can tell some jokes if you want. See, we have plenty of time today. Everything is pre-written. Too fast, doctor. Too fast. Okay, let's slow down. You can slow down. Okay, which one that you want me to re-explain? Which part that you cannot catch up? Too fast. Let us start from the beginning, okay? Let us start from the beginning. In the beginning, there were dinosaurs roaming on the face of the earth. Okay, forget about it. No, that's just a stupid joke. So let's go over this again. Okay, I'm going to go slowly now because we have plenty of time. Okay, we have plenty of time because it's already pre-drawn. So this is the original block diagram. This is the original block diagram. We want to simplify this into a single block. But of course, whatever you do, you cannot change the original block diagram, the representation of original block diagram. Otherwise, you're going to change the system. You are only allowed to perform something that does not change the original block diagram. So, but how are you going to do this? Of course, you cannot see in the beginning. For starters like you, probably you're going to get lost. You're gonna have to do some trial and error. Okay, but seeing here, there's some complicated signal going on here. There is no single item in the block that you can replace, because this is not a feedback loop, because you have a takeoff point in front of G2. You cannot simply just cut this this takeoff point here. You're going to change the original block diagram. But in the table, you can move the takeoff point from behind of the block to the in front of the block. Let's go to our our table here. We have the table. We can move. Let's go back to the table. There. See, you can move a takeoff point from behind the block to the front of the block. This is what we're going to do. If you move that to the front of the block, then you must multiply by 1 over g. 1 over g. So when we move to the front of g2, and therefore we must multiply by 1 over g2 here. We are moving that takeoff point to the front of g2, therefore you need to multiply by 1 over g2 so that you get back the original signal. Okay, I hope that I explained that clearly now. Now to the second stage, after having done that, now you can see this is now just a simple negative feedback. See, you can replace the whole thing with g divided by 1 plus gh, which is the last element in the table. If you look back to the table, the last element in the table, any feedback loop you can replace with g divided by 1 plus gh. See, this is plus and minus, here minus and plus. So normally we have negative feedback, and therefore here we have a plus sign. Okay? All right. Now you can replace that with g2 divided by 1 plus g2 over h1. This is the last element in the table. Now you have two series, two block in series. Let's go back to the table. Where is two block in series? Where is it? There. So two block in series, you can just multiply the two block together. Two block in series. So we can simply multiply G1 multiply with G2 divided by 1 plus G2H1. So you get that. Now again, finally, you have this simple feedback loop, even though your forward transfer function is a little bit complex, and the feedback transfer function is a ratio. You can still replace that with G divided by 1 plus GH, and then simplify. You just want a simple fraction. You want a numerator divided by denominator. You don't want too many fractions. You just want a denominator divided by a numerator divided by denominator. Do you have any question? Now, this may look simple, but sometimes a simplification of block diagram can be quite complicated. See, I have extracted this. Okay, this is not in your notes. There's nothing there. There is the last example, I guess, from your notes. Okay, there's no more. I have extracted this from some tests back then. See if you can think what you're going to do. Oh, sorry. There. Okay. This is an additional example that I have come up with sometime this morning. So let's say you want to simplify this block diagram. This is quite complicated. This is, I bet. Okay, you want a simplification. You want just a single block diagram that relate R and C. I bet, I'm willing to bet money that most of you won't be able to solve this. You won't, but first time seeing this, you won't. How much, doctor? What do you mean how much? How much? What is how much? Oh, how much I want to bet money? No. The solution is already here. Of course, I cannot bet money. I already given you the solution here. See, imagine now seeing this for the first time in your test. Most of you won't be able to simplify this, but but I have already, Doctor, if we have the notes before the classes, we can follow your class while referring to the notes. Okay, maybe next time. Maybe we'll do that. Okay, maybe you can have the notes. Then if I give you the notes, then you don't have to come to class then. How about that? How easy is that? How about I just put everything on e-learning and then you can study my notes, right? I don't have to explain the notes anymore. No, forget about it. Okay. I'll try. I'll try that. We won't understand after that. Okay, so now here, the idea is you're going to have to do some trial and error. You are going to have to do some trial and error. You need to think and crack your head. How are you going to simplify this? So my idea is to move this summing junction from in front of the block to behind of the block. See, I'm going to move the summing junction from in front of the block to behind of the block. If you look at the signal, let's say this is B, this is A. The signal coming here is A multiplied by G2 plus B. So this signal here. So you don't want to change that. You want that to remain A plus G2 even after you have moved the summing junction behind of the block. Okay, let us retrace here. So here this is B divided by G2. So this is A. Signal here is A plus B divided by G2. And then once you multiply by G2, you get A multiplied by G2 plus B. So you see this is equivalent. A multiplied by G2 plus B. So by moving the summing junction behind the block, the signal here remains A multiplied by G2 plus B. See, there's nothing new here. We don't change the original block diagram by moving the summing junction from behind, in front of the block to behind of the block. Okay, you can go back to your table. There's a table. See, you can move this summing junction from in front of the block to behind of the block. So we are going to use that. Okay, so we are moving that summing junction from in front of the block to behind of the block like that. Okay, now you see here this is two summing junction. You can interchange two summing junction. Again, let's go to the table here. There. No, not that one. So this one. So you can interchange two summing junction. You can do that. Okay, now I'm going to interchange these two summing junction. Okay. Now, okay. When we get to here, I'm not going to bet money anymore. This is now it's easy. This is easy. So this is now just two blocks in parallel. It is two blocks in parallel. Let's go back to the table. Two blocks in parallel. Where's two blocks in parallel? There. When you have two blocks in parallel, it is just G1 plus G2 here. So in our diagram here, so this is just two blocks in parallel. One of them is 1 over G, one of them is 1. So you just add them together, 1 plus 1 over G2. And this is all just one long block in series. So you just multiply them and then you get the final simplified block diagram. Just multiply everything and then you can get now the single block. You need to put everything in numerator divided by the denominator. Okay, so that's the end of my notes. Do you have any question? All right, next time I will try to put my notes. The problem is I have just finished my note. Doctor, how to know? Of course you don't know your answer is correct or not. What do you mean how to know your answer is correct or not? Of course it's going to be correct. It is like doing algebra. Let's say x is 2x plus y equal 3, x plus 3 equal some -5. When you solve it, of course you're going to know it's going to be correct. You just need to have some confidence in yourself. Of course, in your test, you won't know whether it's correct or not. But hopefully that we have confidence enough in ourselves that this is correct. I might be wrong. You might find some mistake in my notes. That is normal to do some mistake. All right. So that's the end of my notes for the first hour of this class. If you don't have any question, I think we're going to take a break. We're going to take an early break. So come back here at 4:45 for our next class. Okay, come back here at 4:45. You don't have to copy any notes. I'll put this on your e-learning. All right, so come back here at 4:45. By the end of next class, I will put my notes to your e-learning. See my screen, please type yes in the chat box so that we know that everything is in order. Okay, thank you very much. Thank you very much. All right, so previously we have talked about how we can get a transfer function by simplification of block diagram, and sometimes it can be quite difficult, quite painful to simplify the block diagram, especially when the block diagram is complicated. So there is an easier way for us to determine the transfer function of a system using what we know as Mason's gain rule. But before that, you need to transform the block diagram into a signal flow graph. And then once you have done that, then we can use the Mason's rule to obtain the transfer function. So what is a signal flow graph? A signal flow graph is just consisting of nodes and branches instead of just a block and a branch. So you can see that so this is the usual block diagram. The variable is represented by the branch, and the transfer function is represented by a block. To transform this into a signal flow graph, this is a signal flow graph representation of this block diagram. The variables are represented by nodes. So node X and node Y, those are the variable, and the branch here is the transfer function, which is G. It looks quite similar, but it is not quite the same. So this is a block diagram, and this is the signal flow graph. A variable is represented by a node. There is a signal flow graph. What else? Here. And then it says here, variable at a node is the summation of all incoming signal, and the node variable is transferred to all outgoing branches. So what does this rule number 1 says? Variable at a node is the summation of all incoming signal, and the node variable is transferred to all outgoing branches. So I can illustrate that simply by this diagram here. So now here, this is a node. Yes. Any problem? Yes. Who is speaking? Who is that? Please mute your microphone. Isaac, can you hear me? Okay, thank you very much. The signal at a node here is the summation of all incoming signal. So the value of y here, you can see that x multiplied by m plus c multiplied by 1. So you can see here y is equal to mx plus c. And then the signal at a node will be transferred to all outgoing branches. So P here is 2 multiplied by Y. Q is a -3 multiplied by Y. Even though you have two branches here, you don't split the signal into half. Not half of the signal going to P, another half of the signal going to Q. So the full signal is going to P and the full signal is going to Q. So you can write P is equal to multiplied by Y, Q is equal to -3 multiplied by Y. You don't split the signal. Okay, so that is what we mean by the node variable is transferred to all outgoing branches. See, the summing junction is just a node. A node acts as a summing junction as well. Input node only consists of outgoing branch. Output node consists of incoming branches. Incoming branch. So when you transform the block diagram into signal flow graph, you need to follow all these 4 rules. So the input node can only have outgoing branch. The output node can only have incoming branch. You have to follow that rule when you're transforming the block diagram into a signal flow graph. Okay, let's see here. We have some example here. So draw the signal flow graph of the following control system, A, B, and C here. Can you transform this block diagram into signal flow graph? We have a simple block in series for part A. Okay, so we have two block G1 and G2. So you can simply draw that. Okay, so you can simply draw that there. See? So variables are represented by node. So variable R, you have one node for R. Variable C, you have one node for C. And you connect with a branch, and then that branch represents the transfer function. The directed line segment is we replace a block with a directed line segment. You have an arrow there, arrows showing that the flow of the signal, the flow direction of the signal. So simply that now you have the variable R and the variable C, and you have another variable here. In this case, we have no name for that variable, and then the forward path transfer function is just G1 and G2. Any question? Am I going too fast again? I guess. Let's go slow. Slow down. Slow down. Let me remind myself. Slow down. Okay, so the second part, this is part B. How can we draw the block diagram? How can we draw the signal flow graph representation of this block diagram? Okay, so what do I have here? Okay, there. Okay, so this is the original block diagram. So let us count the variable. Count the variable in the fourth path. 1, 2, 3, 4, 5 variables. So you are going to have 5 nodes in the forward path. One, R is a variable. There's another variable. There's another variable there. There's another variable after the summing junction, and then you have another variable there. So you're going to need 5 nodes. So 1, 2, 3, 4, 5. Oh, sorry. This is. You can represent this just by one variable. Summing junction is just a node. But since we need to fulfill we need to fulfill the requirement 3 and requirement 4. Input node only have outgoing branches. Output node only have incoming branches. So this is the input node R, only have outgoing branches. This is output node C, only has incoming branches. You cannot put C here because now you have both incoming and outgoing branches. Input node can only have outgoing branch. Output node can only have incoming branches. Okay, and then you have a gain of 1 here and a gain of 1 here as well. So you need to put 1 here. There's a missing 1 there. And then you start putting your transfer function. G1 there, G2, and this is the feedback, negative H1, and this is negative H2. So this is the signal flow graph representation of that block. Do you have any question? You need to trace the signal. As long as your signal is the same for both block diagram and signal flow graph, we say that they are equivalent. Okay, let's go to this. Let us go to the last example. Okay, so this is now in part C. Let us transform that into signal flow graph. Yeah, nicely drawn. Okay, so that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you need 6 nodes. 1, 2, 3, 4, 5, 6 nodes. So in this case here, if you look at the output node here, this is quite all right because this is an incoming branch, and you have this incoming branch as well. So you don't need an extra node here because this is already fulfill requirement that output node only have incoming branch. In this case, you have 2 incoming branches. Input node here only have 1 outgoing branch, and the rest just fill in the transfer function G1, G2, G3, G4, negative H2, and negative H1. So that negative here, you have to carry negative H2. That negative also you must carry into your signal flow graph. Now you have negative H1. You need some practice to translate the block diagram into signal flow graph. Now that we are able to draw the signal flow graph, what do we get out of it? After so much trouble, what can we get out of this signal flow graph? See, when you have this signal flow graph, you can simply now use the Mason formula to get your overall transfer function. So what is the Mason gain formula? Okay, so the transfer function of a control system can be obtained using Mason's rule given by the following expression. So the transfer function, which is output over the input, is just given by summation of pi multiplied by delta I divided by delta. So what are they? Pi, delta I is described here. Let me go to delta first. Delta, in mathematical terms, delta is known as the determinant. Delta I is known as the cofactor. But besides that, you don't need to know all the detail about the mathematics of it. So what is P? P is a forward path. What is I? You may have more than one forward path. You may have 2, you may have 3 forward paths. So I is now, if you have 3 forward paths, you're going to have I is equal to 1, 2, 3. For P1, P2, and P3. So P is the forward path gain. What is delta? So delta is 1 minus summation of all loop gain plus summation of all product of two non-touching loops. We'll come back to this later on. Minus summation of all product of three non-touching loop. What do you mean by touching loop? The loop will touch each other if they share a common node. So we say that they are touching each other when the loop shares a common node. What is the delta I? Delta I is the value of delta by discard all the loop gain that touch that particular forward path. Again, I understand that you don't understand any of it, do you? Do you understand or you don't understand any of what I'm saying here? I'm sure that you don't understand any of it. I've been teaching for so long. I already know that. I already know that you don't understand any of that. I'm going to explain this using example. Okay? We will come back to this. Don't worry about it. When the time comes, we'll come back to this. Let's take a look at the next example. Okay. So now we want to find this transfer function. You can do that by simplification of block diagram, but we are not going to do that. We are going to translate this into signal flow graph, and then we are going to use the Mason's formula to get the transfer function. So our task is to transform this into signal flow graph. That is our first task. Let's do that. Okay, so this is the disadvantage of not having the whiteboard. So the blue lines here, the one that I have drawn in blue, is the signal flow graph for this. Okay, so you have one variable there, A, B, and C. R, A, B, and C. Those are the variable. So this is R, A, B, and C. So that node represent A, that node represent B. So you have four variables going forward. You have four variables, R, A, B, and C. Now you just put the transfer function in. Okay, so G1. So here, this is 1. You need to put 1 here. I missed 1 there. 1 here, G1 and 1, G2 and negative H1. So the blue lines represent the signal flow graph. And then we need to determine how many forward paths. P is the forward path. How many ways that we can go from the input to the output? That is called the forward path. So we can go from here, from the input P1, that's the first forward path. You can go and then you go up and then you can go to the output. That's one way. Another way is just you can just go straight ahead. So we have two forward paths, P1 and P2. So the red line, the red dotted line represent the forward path. Two ways you can go from input to the output. So the gain, the forward path gain for P1 is just G2. 1 multiplied by G2 multiplied by 1. The second forward path, the gain for the second forward path is 1 multiplied by G1 multiplied by 1. So that's your P2. P1 is equal to G2, P2 is equal to G1. And then you need to determine how many loops. See, you need to have the loop gain as well. How many loops do you have in your signal flow graph? So now, the green line here represents the loop. So the first loop is the small loop here. There's the first loop, L1. and there's a bigger loop, L2. So the loop gain L1 is G1 multiplied by negative H1. And the big loop L2 is, the loop gain for L2 is G2 multiplied by H1. So you have two loops, L1, G1 multiplied by negative H1, loop 2, G2 multiplied by negative H1. So you have two forward paths and you have two loops. Now you need to determine the determinant, delta. What is delta? Delta is 1 minus summation of all loop gain plus summation of all product of two non-touching loops. So delta is delta is equal to 1 minus summation of all the loop gain, so L1 plus L2, plus the summation of product of all non-touching loops. In this case, loop 1 and loop 2 share a common node. So loop 1 go through this node, loop 2 also goes through that node, so they are touching each other. So we don't have a non-touching loop. So we don't have the product of two non-touching loops. So all we have is 1 minus the summation of all loop gain. So 1 minus L1 plus L2. So there's a minus, so everything is going to be plus. So delta is equal to 1 plus G1H1 plus G2H2. Since we have 2P, we're going to have 2 delta I. See? Delta I. So we have 2 forward paths. So we need to determine 2 delta I, delta 1 and delta 2. The value of delta I is obtained from delta by dropping all the loop gain that touch the ith forward path. You discard all the loop gain that touch that particular forward path. Okay, so delta 1 you get from delta by dropping all the loop gain that touch the first forward path. So you need to go back. So this is the first forward path. Both loop L1 and L2 touches P1. So they share this common node as well as that common node. So you need to drop L2 and L1 from delta to get delta 1. So delta 1 is only 1. You must drop all the loop gain that touch the first forward path. What about the second forward path? So this is the second forward path, straight ahead. Again here, both loop L1 and L2 touch the second forward path. They share common nodes. In fact, they have 2 common nodes. So you need to drop L1 and L2 as well. So your delta 1 is equal to 1, delta 2 is equal to 1 as well. Now with all that, you can now determine the overall transfer function. The overall transfer function is just P1 delta 1 plus P2 delta 2 divided by delta. So the whole thing here now, this is your overall transfer function. G1 plus G2, because delta 1 is equal to 1, delta 2 is equal to 1 as well. And then divided by the determinant delta, the whole thing here. 1 plus G1H1 plus G2H1. I know you have many questions now. You can start asking a question if you have any. We are going to have example after this where the 2 loops are not touching each other, and we are going to have another example where one of the loop does not touch any forward path. So G1 and G2 cannot be a loop. What do you mean G1 and G2 cannot be a loop? No, G1 is just one segment. So a loop, when you start at a node, you go around and come back to the same node. That's called a loop. G1, you just go forward, that's not a loop. G2, you just go forward, that's not a loop. A loop is when you start at a node, go around, come back to the same node, that is called a loop. Do you have any other question? A loop is when you start at a node, coming back to the same node, that is considered a loop. All right, so let us go to the next example. Okay, next example. Okay, this example is friendly. It already gives us the signal flow graph. You don't need to draw the signal flow graph. It's already given. How nice is that? All you have to do is use Mason's rule to determine the transfer function. Okay, first you need to determine how many forward paths, how many ways you can go from input to the output. You can go forward, straight ahead, G1, G2, G3, G4, G5. There's one forward path. The second forward path is G1, G6, and G5. So you have two forward paths here. How many loops do you have? You have one loop here, G2 minus H1, that's one loop. And there's another loop here, G4 minus H2. So you have two forward paths and two loops. Some of you might want to consider this as a loop. No, you cannot go, this is one way. This is one way. You cannot go back through G3. Look at the arrow there. In this case, you only have two forward paths, and then you have two loops. Furthermore, loop 1 does not touch loop 2. So in this case, we have a non-touching loop. They do not share a common node, therefore, they are considered as a non-touching loop. Loop 1 touches the first forward path as well as the second forward path. Loop 2 also touches the first forward path. It also touches the second forward path. So with that, we can now use the Mason formula to determine the transfer function. Okay, so we have two loops, two forward paths. G1, G2, G3, G4, G5, that's the first one. The second one is G1, G6, and G5. Okay, we have two forward paths. We have two loops. Loop 1, G2, negative G2H1. Loop 2, negative G4H2. Two loops. Now delta is 1 minus the summation of all loop gain, minus minus you get plus the summation of product of two non-touching loop. Since L1, L2 do not touch each other, so we need to have a product of two non-touching loop. So that's your delta. So delta is 1 minus summation of all individual loop gain plus summation of all product of two non-touching loop. So we have one product of two non-touching loop, L1 and L2. And what is delta 1 and delta 2? Since we have two forward paths, we need to have delta 1 and delta 2. Since L1, L2 touches the first forward path, you need to drop all the loop gain that touches the first forward path. Therefore, you have 1 for delta 1. P2, both loop also touch the second forward path. So you need to drop all the loop that touches the second forward path. Therefore, you get 1 again for delta 2. And then now you can use the Mason's formula. The overall transfer function is just P1 delta 1 plus P2 delta 2 divided by delta. So this is your overall transfer function. Do you have any question now? Can repeat from delta 1. Okay, delta 1, the value of delta 1 we get from delta with all the loop gain touching the first forward path are discarded. You must drop all the loop that touch delta 1. You get delta 1 from delta by dropping all the loop gain that touch P1. So in our case, both loop touches P1. So this is forward path. So both loop share a common node with P1. Therefore, you need to drop both L1 and L2 from delta. Delta 2 also, when you want to compute delta 2, you must drop all the loop gain that touches P2. This is Pi here. When I is equal to 2, you need to drop all the loop gain that touches P2. So in this case, again, both loop share a common node with P2. So this is P2, G1, G6, G5. The first loop share a common node here. So you need to drop L1. The second loop share a common node there with P2. So therefore, when determine delta 1 and delta 2, you need to drop L1 and L2 for both delta 1 and delta 2 because both loop touches P1 and P2. After this, we are going to have an example where one of the loop does not touch one of the forward path. Do you have any more questions? All right, so let's go to the last example where one of the loop do not touch the forward path. Okay, here. So we have this block diagram. You can see this is a loop there. The small loop here will not touch this upper forward path. But okay, let us draw the signal flow graph representation of this block diagram first, and then we can now determine the transfer function. Okay. So this is the signal flow graph. You have two forward paths straight ahead, G1, G2, G3, and then you have this G4. You have two forward paths, and you have two loops. You have two loops here. G2 negative G2H1, negative G2 G3H2. You have two loops. But you see, loop 1 here, loop 1 does not touch forward path number 2. Okay, so what is delta? Delta is 1 minus the summation of all loop gain plus the product of two non-touching loop. So L1 and L2 touch each other here. So loop 1 and loop 2 share a common node here. So there's no product of two non-touching loop. So you only have the summation of the two loops. But now, since you have two forward paths, you need to have two delta. So delta 1, both loop touch the first forward path. Again, you need to drop that from your delta to get delta 1. So delta 1 is only 1, but delta 2 here, L1 does not touch P2. L1 does not share a common node with forward path P2. Therefore, you do not drop L1 from your delta to get delta 2. So delta 2, you do not drop this L1, but you drop L2 because L2 touches second forward path P2. So with that, you can now determine your transfer function. Your transfer function is just P1 delta 1, P2 delta 2 divided by delta. So that is your overall transfer function. Okay, so that's the end of my notes. I will post this note to your e-learning. You don't have to copy any notes today. If you have any question, you can type your question in the chat box, or you can just unmute yourself and ask your question. Can you repeat about the delta? Is it necessary to write 1? Yes, this one is necessary. What is delta? What is delta? You go back to the definition of delta. This is delta. Delta is equal to 1 minus summation of all individual loop plus summation of all product of two non-touching loop. If there is no non-touching loop, then you don't have that term. If you have the product of 3 non-touching loops, then you have to minus that as well, and so on and so on. It goes on and on and on and on. If all the loop touches each other, then all you have is just 1 minus summation of all individual loop gain. That's for the delta. You need to look for the non-touching loop, and you need to take the product of that. You need to multiply the loop together and put in this parentheses. Any other question? All right. So that's the end of the class today. When is our next class? Tomorrow. Okay, tomorrow. I will try to finish my notes and put notes for tomorrow in the e-learning. I'm going to stop my presentation here.